Okay, so today we're going to derive the speed of light through Maxwell's equations, and we're going to use the differential forms of his equations, which are right here. We have the del, the divergence of the electric field is equal to rho, which is the charge density, divided by epsilon naught. We're also going to have the divergence of the B field. The field is just equal to 0. We're going to have the curl of the electric field is equal to minus d over dt of B. So basically the time rate of change of the magnetic field. Now we have Maxwell equations, the fourth one, which is also the longest one, is equal to mu naught times current density times mu naught plus epsilon naught times mu naught, because this is factored, d over dt of the electric field. And it should be noted two things: that these come from the divergence theorem, and these come from Stokes' theorem. Give you that little hint if you guys want to try and figure them out, derive them from those theorems. I do think you need Calc 3 for this video to understand it probably more in depth, but I think it still makes sense. Now I'm going to draw the right on top the wave equation, which is a very useful equation. Anything that solves this equation is defined to be a wave. So we're going to take this is the second time rate of change of some function which is a wave. So just this would be up here would be d squared dt squared, which is just equivalent to this. I'm going to generate it like this, and it's going to be v squared, and this is just going to be psi, and I don't know if you guys can hear that, but that is my cat. She really wants to come in my room right now. See, psi. So that's all this is. So now we know that. We'll leave that there for reference, and then we're just timesing this entire thing by v squared. So I'll just leave it like that. Let me box these things off, and we'll box this off. So we have these, and we're going to start off by using this one, and then we're going to use this one. And basically what we're going to do is we're going to compute the velocity of the electric field, and then the velocity of the magnetic field, and then see how whenever you get a changing electric field, you get a changing magnetic field. So we're going to start by taking the curl of the curl. So we're taking the curl of this, of the electric field, which is equal to the curl. I just want to keep it algebraically, the logic one. We want the logic to be good. Just keeping it algebraic logical, I guess. And we're going to have to know this identity too. So basically, if you take the gradient of the divergence of some vector field, it's going to be take the gradient of the divergence of a vector field minus the Laplace, which is just the del operator squared, of the vector field. It's going to be equal to the curl of the vector field. You don't actually have to memorize this. I don't think anyone really does. I, for some reason, know this. I also like to show people this proof. It's pretty interesting. So let us continue. We're going to basically sub this in here, and we're going to get divergence. I'm going to gradient of the divergence of the electric field. Oops. Minus Laplace of E, and we can see that we take minus d dt out and take the curl first. So the curl of B. Okay, so we see right here that we're going to get this function. Right? This is just this. This is the same thing. I'm not going to write a vector hat in all of these. This is a pain. But basically, we're going to know this is an oscillating electric field. We're looking at a wave, right? And in a vacuum, we're not going to have any Q enclosed, so rho is 0. Right? That's another way to look at it. So we're not having, right? It's just some electric field traveling. There is no Q enclosed. So since Q equals, you remember from his integral forms equation, is proportional to rho. Since Q is 0, rho is 0. So this is going to be 0. And we're left with this part. And we're going to take the minus d over dt. We'll drop the negative signs in the next part, but we're going to see that this is just this. So we're going to use this, mu naught j plus epsilon naught d over dt of the electric field. Okay, so basically now we have to look at is, what is j? Well, we're in a vacuum, right? So we're in a vacuum, there's no current. So this term again is 0. So, I don't know, I said it again, but just like this term, that term is 0. So we're going to be left with this some changing electric field, right? We have no current changing, so it's all going to be 0 too, with respect to time. So we can, again, we can drop the negative signs. It's going to be equal to minus d over dt of mu naught epsilon naught d over dt of the electric field. Now, what's going on here? We see that clearly we get the second derivative with respect to time of e because we can factor this out. So let us finish writing this. Is equal to, I don't know why I forgot to drop the negative sign over here. Let's get rid of that. And then we're going to get mu naught epsilon naught d dt of this. Now we're going to do the same thing for this one. So I'm going to do this in now we're going to do this in red. So we're going to take the curl of the B field is equal to the curl of mu naught j plus epsilon d over dt of E. And we're going to see again that this term is 0, and this term is going to become this term. So we're going to do gradient of the divergence of B minus the Laplace of B is equal to, well, we're going to again, this term is going to be 0. We're going to get mu naught epsilon naught. We can, I'll do it out. So we're going to get D. Oops, I forgot. I'm going to factor out the mu naught epsilon naught. Mu naught epsilon naught, the curl of D through dt of E. Well, we know that magnetic monopoles don't exist, which is right here, so this is going to be 0. Very strange thing that they don't exist. But they don't. Oh, my computer lagged out a bit. Is equal to, we can also take out d dt and take the curl of E. So we can take d over dt, take the curl of E first, cross E, and we know that that's just this. And we see clearly the negative signs are going to drop. We're going to get the second time we're going to change with respect to B. And let's write this right next to it. So we're going to get squared of B, the Delaware square, is equal to mu naught. I do apologize for my monotone voice today. I'm pretty tired. I have a massive headache. Yeah, so basically right here, we get negative sign, the negative sides are going to drop here. We're going to get the second time we're going to change of the magnetic field. So we're going to get d squared over dt squared of the B field. So we've just derived some beautiful, beautiful, beautiful equations right here. See, these are wave equations. Right? What is the difference between this and this up here? Right here. Well, we had this, it's written, backwards. And then we also have, if we divide by 1 over v squared, we get this, the exact same format here. So we see that in this case, we see that v is equal to 1 over the square root of mu naught epsilon naught. And I encourage you to try this. Basically what you do is you just, divide by 1 over, you divide by mu naught epsilon naught on both sides. You'll get 1 over, you get the del squared of E, the Laplace of E. divided by mu naught epsilon naught is equal to this right here, which is just in case we have E, the time rate of change of E, the second time rate of change of E. So that's really it. There's much more to it. We just derive the speed of light. So we're gonna have E x, so it's gonna be oscillating in the x direction, up and down. We some initial, right? It doesn't really matter what. Cosine omega t minus kc, and then we're gonna have we're gonna basically look at what does this create a magnetic field? Well, let's see if we can come up with something. Well, we know this equation. So we know that if we take the curl of E is equal to minus d over dt of B. So let's take the curl of E. So if you don't remember, you stick this in a determinant or something like that, whatever you guys want to do. You just use, there's a lot of tricks to cross products. And we're going to get EX, and this is 0 and 0. There's no oscillation in either of those directions. So we're going to get basically that if you take the determinant, well, you get I hat, we only get a y hat direction. And we're going to get the partial of z of E of x y hat, which is just if you differentiate this with respect to z, you're going to get k sine omega t minus kz, which is also equal. So that is the curl. This is in the also got my direction because curl gives you a vector is equal to minus d over dt of b. So we can now, what we can do is, let me write it like this, more logical later on, b. We can integrate both sides. So we're going to get minus db dt dt, right, is equal to the integral of E naught k sine omega t minus k z, which is in the y hat dt. This will give us, minus b is equal to, if we integrate this, k over omega, and this is going to be cosine omega t minus kz, and we see that our vector component is in this direction. So basically what we got is we got the same electric field divided by times k divided by omega. So if we remember waves, we know that velocity is equal to lambda times frequency, which is just lambda, which is wavelength divided by the time it takes to complete a. So you have some wavelength here, and then period is from to go to here, which makes sense, right? Velocity is just going to be that. So that's actually also equal to omega divided by k, which is also equal to 2 pi divided by t divided by 2 pi lambda, and we see that is lambda over t. So just just for quick proof. So we're gonna get that this is also equal to b is equal to E naught. Well, we found out that v is c, right? Cosine omega t minus k z y hat. So let me write this up here. So we get a b, which oscillates in a y direction, is going to be our initial divided by c, which is the initial the magnitude of the electric field vector. Cosine, and this is actually in the x hat direction, like that. So omega t minus k z y hat. There we go. Now let's draw our oscillating field. We see it's going to oscillate, technically going to start at this max, and then we'll write this here, because it's cosine. That's good enough. It's not to scale. Also not the best at drawing, and we're going to see it's going to go up and down. And then we're going to get a B oscillating in the Y direction, but traveling in the Z direction and T direction. So, boom. There's also another out of scale because, you know, the B field should be substantially smaller than the corresponding E field, which is really interesting. And we see that these are orthogonal. And that's really all, and this goes at C. There we travel at the speed of light, which we just found above. And this is really the proof. I just think it's interesting that when you have an oscillating E field, you always get a B field. Thank you guys so much for watching, and that's all I have for today.